Last time, we built a tiny database engine, but it had one major problem. Every query had to scan through every row. Today, we're going to fix that by building a tiny database index. Before we build an index, we need to understand the problem it's solving. Let's imagine our database contains just a handful of users. If we want to find Alice, our database starts at the beginning of the table and checks each row one at a time. Is this Alice? No. Is this Alice? No. Is this Alice? Yes, we found a match. With only a few rows, that's not a big deal. The query finishes almost instantly. But now imagine our database contains 1,000 users, or 10,000, or a million. The database still has to use the exact same process. It starts at the first row and keeps checking rows until it finds what it's looking for. The more data we have, the more work the database has to do. This approach is called a table scan because the database scans through the table looking for a match. And sometimes it doesn't even find one. Imagine searching for a user that doesn't exist. The database would have to check every single row before it could confidently say, "No match found." This is one reason database performance becomes such an important topic as applications grow. A small database might feel fast enough. A large database can become frustratingly slow if every query requires scanning thousands or millions of records. So the question becomes, can we create a shortcut? Can we build a way for the database to jump directly to the information it needs instead of searching row by row? That's exactly the problem database indexes were designed to solve. And we're going to build one ourselves. An index is one of the most important tools a database uses to speed up queries. Basically, an index is a lookup table. Instead of searching through every row one at a time, the database keeps a separate structure that helps it find records much faster. Think about the index at the back of a textbook. If you wanted to learn about databases, you could start at page 1 and read the entire book until you found the section you needed. Eventually, you'd get there. But it would take a long time. Instead, you open the index, find the word database, and immediately jump to the correct page. That's exactly what a database index does. It provides a shortcut. In our tiny database, we're going to build an index that maps a user's name directly to that user's record. Instead of searching through every row looking for Alice, we'll be able to ask the index for Alice and get the answer immediately. Notice that we're not replacing the table. The table still stores the actual data. The index simply helps us find that data more efficiently. You can think of it as a directory or a map. The table holds the information. The index tells us where to look. Of course, there is a trade-off. Because we're storing additional information in the index, we'll use more memory than before. But in exchange, our queries can become dramatically faster. That's why most real databases use indexes extensively. Next, let's build our own index and see how surprisingly simple the core idea really is. Now that we understand what an index is, let's build one and immediately put it to work. In our original database engine, all of our data lived inside a table called users. That table isn't going away, it still stores the actual records. What we're adding is a second structure called an index. At the top of the file, we create a new map called nameIndex. A map is perfect for this job because it stores key-value pairs and can retrieve information very quickly. In our case, the key will be a user's name, and the value will be the user record itself. Now let's look at what happens when we insert a new user. Previously, we only added the user to the table. Now we're going to do one additional step. After creating the user record, we add an entry to the index. The user's name becomes the key, and the user object becomes the value. So if we insert Alice, the index stores a shortcut that points directly to Alice's record. If we insert Bob, the index stores another shortcut that points directly to Bob's record. As our table grows, our index grows alongside it. Every time we add a new row, we update both structures. The table stores the data. The index stores shortcuts to that data. Now, let's see why that's useful. In our original database engine, the findUserBy function had to scan through every row in the table looking for a match. With an index, we can skip that process entirely. Instead of searching the table, we ask the index directly. When we call nameIndex.get and provide a name, the map immediately returns the matching user record. No loop, no filter, no table scan, just a direct lookup. That's the power of an index. We're no longer searching through the data. We're using a shortcut that was prepared ahead of time when the data was inserted. Notice that the code is actually simpler than before. We've replaced an entire filtering operation with a single lookup. Of course, the improvement becomes more noticeable as the database grows. With 3 users, both approaches feel instant. With 1 million users, the difference between approaches can be dramatic. The table scan version may need to examine row after row after row. The indexed version simply asks the index for the answer. Now let's run the application and see our indexed database engine in action. Open a terminal in the same folder as your project and run the application. As before, the database starts up and inserts several users into the table. But this time, something extra is happening behind the scenes. Every time a user is inserted, an entry is also being added to the index. The table stores the records. The index stores shortcuts to those records. Next, we perform a lookup for Alice. Previously, this would have required scanning through the table row by row until a match was found. Now the program simply asks the index for Alice's record. The index immediately returns the result. The answer is already organized in a way that makes it easy to find. With only a few users, the difference may not seem dramatic. But imagine scaling this database to thousands, millions, or even billions of records. The indexed lookup still works the same way. Instead of checking row after row, the database uses the shortcut we created. That's why indexes are one of the most important performance tools in modern databases. They're a simple idea, but they can have an enormous impact on how quickly data can be retrieved. And now you've built one yourself. Let's quickly recap what we built. In our first database engine, every query required a table scan. The database had to look through rows one at a time until it found a match. That works well for small amounts of data, but it becomes increasingly expensive as the table grows. To solve that problem, we introduced an index. The table continued storing the actual data, while the index stored shortcuts that help us find that data quickly. We used a JavaScript map to create those shortcuts. Whenever a new user was inserted, we updated both the table and the index. Then, instead of scanning through rows with a filter operation, we performed a direct lookup using the index. As a result, our queries became both simpler and faster. More importantly, you've learned one of the most important ideas in database design. Indexes improve read performance by storing additional information that helps the database find records more efficiently. Of course, there is a trade-off. Indexes use extra memory and must be updated whenever data changes. But for many applications, the performance benefits are well worth the cost. Today, you didn't just learn what a database index is. You built one yourself and saw exactly how it works behind the scenes. If autism-friendly coding tutorials like this, where we demonstrate software concepts with real examples, are helpful, subscribing is a great way to find your way back here. If you'd like to support the channel, I also have resources available on Patreon, including coding affirmations and the AutistiCoder reference guide. You can find them at patreon.com/AutistiCoder. Thank you for watching, and let's keep learning and growing together.